This is part 3 of the acid-base calculation notes. In this section of the notes, we are going to focus on weak acids. This says and bases. We're really focusing on weak acids. I said in the previous set of notes that we are only going to be looking at strong bases. And just as a refresher of those strong acids and bases, strong acids and bases, those strong acids dissociate one hydrogen ion completely in water. And so we get a non-reversible dissolution reaction, or just a non-reversible reaction where any strong acid is going to disassociate that one hydrogen, and we aren't going to have any of that compound left. For a strong bases are going to dissociate all of their OHs, so like that barium hydroxide is going to disassociate all of it, the hydroxide ions. And again, we have a non-reversible reaction if we look at like the sodium hydroxide example, because those are all dissociating with that. So that strong means we know that it completely dissociates. We would have an equilibrium constant, a K value that's product favored with that complete dissociation. But we are only going to use strong bases in this course. So as we discuss our our weak acids, all of this is going to would apply to bases as well, following the same kind of changes or differences with bases above. We're just going to focus on weak acids. For a weak acid, acids dissociate one H plus hydrogen ion at a time. And these end up being reversible reactions because our weak acids don't ionize completely. So if we look at HF, which is a weak acid, we see it's a reversible reaction, just like when we were talking about solubility, something slightly soluble, where it's going to ionize one H plus, or some of the H pluses and some of the fluorines, but some of those are also going to stay in that compound, still in that aqueous solution, but not separated into ions. And so we see that as reversible. We're still only dissociating one hydrogen. So if we have H2SO3, one H plus is going to break off. The other H is left with that SO3 with a -1 charge now. And so because those weak acids don't ionize or dissociate 100%, we can't assume that that H plus is going to equal the concentration of our acid. And I should have specified on here because with a strong acid, our Ka is greater than 1, but with a weak acid, our Ka is less than 1. And remember, any of those equilibrium constants, like KEQ, that's concentration of products over concentration of reactants. Well, if we have something that's less than 1, that means that whatever is in the denominator is going to be favored, so our reactants. And so with these, we have most of that doesn't ionize. We have some of it ionizing, and so it's weaker because there are less hydrogens for us to classify. And we know that our classification of pH is based on those H plus ions with that. And so again, as we look at weak acids, we had said if we have those Ka values greater than 1, those are our strong acids. Well, now as we look at those Ka values that are less than 1, these are all of our weak acids. And we can't just then, checking that Ka value, we can't just say, okay, whatever my concentration of my solution, it's not going to completely ionize. So I'm not going to have that same concentration of H plus. So then we need to look at this as an equilibrium problem. And then to find that H plus, we have to go through, we write out that ionization or dissociation equation. The difference from our solubility is that HF, or our acid compound, is aqueous, and so it is dissolving. It's just how much is breaking into ions with that. And so all of these are aqueous when we're talking about those weak acids. So we write that ionization or that dissociation equation showing how it would break up, or what does break up. Then we're writing that expression. And so instead of writing a KSP expression or a KE expression, we call it a KA expression, but it's still going to be our concentration of products over concentration of reactants. Nothing has changed. It's just we're talking about equilibrium of acids with that. And then, we go through, and this is the same problem as a KSP problem, because we're going to have information about our concentration of our acid, which is our reactant, but we're also then going to have information about our Ka value. And so I'm given those Ka values and I can plug that in and I'm able to find information, just like we did with solving a KSP equilibrium problem. So that Ka value, again, is telling us the ratio of our products to reactants, just like in our equilibrium unit. And we have now on the back of that formula sheet, I didn't reference them before when we were looking at the formula sheet. We have our formulas here, but then we also have these Ka values on the back. And so we have those to tell us if it's a strong or a weak acid. And then if it's weak, we need to use that in our calculation. So what does this kind of look like to kind of give us a little better understanding? So that ionization, again, breaking into ions, how does that compound break into ions? So for a weak acid, so this is showing the ionization of a weak acid. I didn't show two with those. So not ionizing fully. So we're looking at oxalic acid, and with that, that has that constant ionization constant, which would be the Ka of 5.6 times 10 to the negative 2. So because that Ka is less than 1, that means that it is going to be reactant favored. And so as we look at this, we have that aqueous compound, that oxalic acid, reversible reaction. Well, as we look, we are going to have very little ionization. Most of this is staying as that compound. So if we had 2 moles at the start, 1.7 is going to stay in that compound. And then we have very little that is that hydrogen, and we have very little that is that C2H04 minus ion, like that. But notice that we still do have 1 mole of H plus, 1 mole of C2H04. And so we are going to still be able to think of this as like we have 1X and we have 1X when we are looking at how can we get one variable to solve. So if we consider, again, similar to what we've done in the past, how can we look at these? Well, if this is not ionizing completely, this is, again, we have, here's my reactant, here are my products. This is reactant favored because I have that higher concentration than of my products. And so we are going to have that HC2H04 is going to be favored when we have that Ka value of less than 1, showing how it's sharing space. Our products, well, this is an acid. It's going to dissociate 1 hydrogen or ionize 1 hydrogen, and then we're left with C2H04 with a -1 charge because we lost 1 hydrogen with that. And so we can show that this is reactant favored by showing, again, how it's sharing space. And we are going to have less of it that has ionized. All right, so differences from our KSP is that this is aqueous. We are going to have to take into account what is the concentration of that solution in order to figure out, well, how much of that, what is actually our H plus concentration, which is what we need if we are going to then go through and do acid-base calculations. Reminders of sig figs. And as we're going to calculate pH and pOH, those are unitless numbers, so we wouldn't have a unit on the end, but concentrations, square brackets means concentrations, those concentrations need units of molarity. So we can see here all of these concentrations, whether it's an OH concentration or an H plus concentration, those all have units of molarities. And concentrations we've been using, same sig fig rules as always. If it's in scientific notation, we're just looking at the leading number. 2 digits after the decimal, or zeros after the decimal, are significant if there are digits to the left. So then that is 4. Zeros to the left are not significant, even if there's a decimal, so that one's 3. But again, that pH scale is a 1 to 14 scale. How is 3.789, where it is showing that same exactness, but 13.789 showing that same exactness, those have the same sig figs. And so for pHs, it's only after the only digits after the decimal that are significant. And so each of these have 3 sig figs. Again, it's that scale goes from only having 1 digit from the decimal to 2, but we want to show that those are still significant. Something like POH, 1 digit after the decimal, so that would have 1 sig fig. All right, so we should already know how to use these formulas if we have one piece of information. If I have a pH, I can find H+, and then I can use this. If I have an H+, I can find pH, and then I can use this, and we can go between, depending on what we have to start with. So you should be familiar with these. They're on the back of your formula sheet. So now how do we get to having a piece of this information? So if we're calculating those 4 pieces of information for an acid or a base, we need to find one of these. So calculate those for a 4.3 times 10 to the negative 2 molar solution of nitrous acid. So I have an acid, I have its concentration. Let's look at writing the chemical formula. So nitrous acid, that OUS ending means that's coming from a polyatomic with an ite ending, which would be that nitrite, because we have that root, and I did not spell that right. And as we look at it, it's an acid, so we have a hydrogen ion with a +1 charge. Nitrite is NO2 with a -1 charge. Drop and swap to make that neutral. This is HNO2 as our acid. Next step is I have the concentration. So we have that the concentration of that HNO2 is 4.3 times 10 to the negative 2 molar. I have that piece of information. If this is strong, I know that's how many, the concentration of hydrogens, but if it's weak, I don't know that. So let's check the Ka formula. So going back a couple of slides or on the back of your formula sheet, I'm finding my HNO2, which is right here. Well, my Ka value is 5.6 times 10 to the negative 4. I'm going to write that in. Remember, Ka values or any K value doesn't have a unit on it. And is this strong or weak? Well, this Ka is less than 1. And remember, any of our K values is products over reactants, with that going to be favoring the solid. This is a weak acid. And so if it was strong, there we go. This is a weak acid. If it's strong, then we know this concentration is the hydrogen ion concentration, but it's not. It's not going to completely ionize. And so I need to write that ionization or dissociation equation and then my equilibrium expression. So writing that equation, we look at our compound HNO2, and that is a solution. Reversible reaction, well, it's an acid. It's going to ionize 1 hydrogen into the solution, and then whatever is left is going to have a -1 charge because we lost a +1, so that's how we get a -1, and that's going to be in the solution. So that's my equation, ionizing off 1 hydrogen. So let's write our equilibrium expression, our K expression. Because it's an acid, that's what makes this a Ka. So my Ka is concentration of my products, what gets produced, those are my ions. So I've got H+ times NO2 -1 concentration, square brackets mean concentration, and then that's all over HNO2. This is aqueous because it is a solution already. It's not like our solubility where it's not dissolved. It's all dissolving. It's just not all breaking into ions. So there's my Ka expression. So now what do I need to find? Looking at these 4 pieces of information, well, I have this H plus in this Ka expression. So do I have enough information that I can solve for that? Well, I went to my formula sheet and I have a Ka value, so I could plug that in. I also know the concentration of my nitrous acid solution is that 4.3 times 10 to the negative 2. That was given to me in my problem, so I can plug that in there. So as I look at this, I have this information, I have this, I'm looking for this, but if I don't have this, I do know that I have one H plus and I have one NO2 minus. And so we can use our same idea of the mole ratio as we did with our KSP problems, and I can plug that information in. I can take that 5.6 times 10 to the negative 4, and that's going to equal, I can plug my HNO2 in on the bottom, and then I'm looking for H plus, but I know that I have one H plus for every one NO2. Because these always dissociate only one H plus, the nice thing is that's always going to be the case, because then we can say, okay, this is 1X, and my NO2 is going to be another X with that. And so we get that kind of X squared from, here's my 1X, here's another 1X, and now I have an equation that I can solve for that one variable that I have. So I'm going to go ahead and do that. We've got, as I look in here, so I've got that 5.6, and I'm going to actually change the top. That X times X is X squared. And so we're solving for that X squared. How can I do that? Well, I'm going to multiply both sides by 4.3 times 10 to the negative 2. That's going to cancel. So that's going to give me X squared equals, and then when I multiply those two together, I'm not going to do any sig figs until the very end, and then we'll talk about those. I've got 2.408 times 10 to the negative 5th, keeping that number in my calculator. And then how do I undo a squared? I'm going to square root both sides. And so we end up with X equaling 4.907 times 10 to the negative 3. Let's look at what we plugged in for our calculations. With our strong acids and bases, we only have our concentration that is in our problem. We though do have, if we look at what did we plug in over here, we do have our 5.6, that's 2 sig figs, and our 4.3. So we are going to take into account that we have 2 sig figs in our Ka and 2 sig figs in our concentration of our solution. And so we are going to keep 2 sig figs. This is a concentration, so I'm going to keep that 4 and that 9. So X is going to be 4.9 times 10 to the negative 3. And that is representing a concentration, so that is a molarity. And what is that equal to? Well, that is equal to our H plus. It's also equal to our NO2 minus concentration. But really the one that we care about is the fact that that is that H plus concentration, because now I have that piece that I can use to start the rest of my calculations. So I have that H plus is 4.9 times 10 to the negative 3 molar, and I can find the rest of this information. Well, if I have H plus, I know this value, then I can go ahead and find that pH. So pH is going to equal the negative log of that 4.9 times 10 to the negative 3. Plugging that into my calculator, I get, and I'm going to again look at sig figs, 2.31. We've got those 2 sig figs from our 4.9 When we switch to a pH though, remember only digits after the decimal are significant. Next, now that I have pH, I can go ahead and cross over to getting that POH. So pH plus POH equals 14. And I can go ahead and rearrange that, plugging in my pH value that we just found. So 14 minus that 2.31 is going to give us a 11.69. Again, 2 sig figs, that's our POH. And then our last step would be, well, now I have my POH, I can find my OH, hydroxide ion concentration. So 10 to the negative 11.69, and that's going to give us, we're going back, we still have 2 sig figs, but now my sig figs are all of my digits, 2.0 times 10 to the negative 12 molar. So after we found that H plus concentration, then we just go through and use our formulas like we did for when we were doing strong acids and bases. It is just finding that H plus takes a little bit of work, and then we can go from there. All right, so calculating this information for phosphoric acid, for carbonic acid is next. If you want, go ahead and press pause and try this on your own if you want to get started. Otherwise, follow along with me. All right, so now we are looking at a 0.0670 molar solution of carbonic acid. And again, like this is an acid looking at carbonic, so that would be carbonate, which is CO3 with a -2 charge. It's an acid, so it's pairing with a hydrogen. So we're going to have H2CO3. Going and checking our Ka values, I see that my Ka value is 4.5 times 10 to the negative 7 from my formula sheet. That is less than 1, which means that this is weak. And so now we need to write that ionization equation. So we have our H2CO3, which is aqueous, double-sided arrow, because only some of that is going to ionize. It's going to break off 1 hydrogen, leaving us with HCO3 -1, which is also aqueous. So writing that equilibrium expression, it's a Ka because this is an acid, but same process as a KEQ. Concentration of products, H plus concentration times HCO3 minus over concentration of reactants. That's the concentration of our H2CO3. And now we can go ahead and we need to find one piece of information that is going to help us to find the rest. So we're going to always be finding that H plus first. So that's our goal. Well, how do we find that? We can plug in the information that we know. I have a Ka value, and my problem told me my solution's concentration is that 0.0670. And so let's go ahead and plug those in. So I've got my Ka, which is that 4.5 times 10 to the negative 7. On the bottom, I've got the concentration I was given in my problem, 0.0670. And looking at the top, well, I'm finding that H plus, but this is always a 1-to-1 ratio. And so with that 1 H plus and then our one other ion, we are always going to get that X times X, which is X squared. So we can always anticipate that because of the fact that that 1 H plus is going to ionize. And now we get to go through and solve. So I'm going to solve. I'm going to multiply both sides by that 0.0670 to get the X by itself. So then we get that X squared equals are 1 point, oh, actually, I don't know what that equals. So we're going to then have to do square root of both sides. So we get that 4.7 times 10 to the negative 7 times 0.0670. That equals x squared, and then square root both sides. And so when you plug all that into your calculator, we'll get 1.683, that keeps going, times 10 to the negative 4th. Let's look at what sig figs we want. We had both our Ka value and our concentration in here. And so as I look at those values, well, my Ka value has 2 sig figs. My concentration has 3 sig figs. I want what is the least of those. And so 2 sig figs is what we're going to want. So we're going to keep that 1.68, so that 8 is going to round that 6 up. So I'm going to have 1.7, 2 sig figs, times 10 to the negative 4. That's my x value, but x represents that H plus concentration. And so now I have that information that I can find my 3 next pieces. And again, we kind of just go through with these weak acid problems, because we're always finding H plus first. That next steps we take are always going to be similar. So now that we have that H plus, we can find pH. So pH equals the negative log of that 1.7 times 10 to the negative 4, which is going to be 3.77 when we plug that in our calculator. 2 sig figs, because with pH, sig figs are just digits after the decimal. Now that I have my pH, I can go on and, well, where else is pH? I don't need my H plus, but I see pH here, so I'm not going to use that one. But I do need to find my POH, so that POH is going to be 14 minus my 3.77, and 14 is exact, so we keep whatever digits after the decimal that our pH had, so 10.23, and again, that's maintaining our 2 sig figs, digits after the decimal for pH and POH. So then I found my POH, I found pH, so now finding that OH concentration, well, to find that OH concentration, I'm going to go negative 10 to the negative 10.23 to get that OH concentration. And when I plug that in my calculator, I get 5.9 times 10 to the negative 11. That is a concentration, so it does need the molarity unit on it. And again, 2 sig figs, now that we have a concentration, all of the digits are significant, and so keeping that digit in front of the decimal does end up being significant with that. All right. So if you would go ahead and give number 11 a try. If you get stuck, maybe rewind to that part in the in examples 10 or 9 to kind of go through and follow that process. I have the answer for number 11 worked out here for you. So check your answer as you go through. This didn't provide the steps, so see if you can practice how you would think through that problem and you would get those answers. For practice, there is a acid-base calculation worksheet that has both strong and weak calculation problems on it. Reach out to your teacher with any questions.